So in section 2, we're going to be talking about another new set of identities called the power-reducing identities. And what the power-reducing identities allow us to do is take a degree 2 trig function and rewrite them as a double angle. So these are the 3 identities. And again, we usually typically never going to write down the identities for secant, cosecant, cotangent, because what are they just going to be? The reciprocal of what we've written here, right? So like, typically we don't waste our ink to write the other versions. You can if you want, but so one of the things that we'll do with these is to use them to like find the exact values. So PR is just power reducing. So let's say we want to do sine squared of 3 pi over 8. So if I want to find the exact value of this as it's currently written, I'd be out of luck just going to the unit circle because 3 pi over 8 is not a unit circle value. However, if I plug this into my power reducing, that would be 1 minus cosine of 2 times 3 pi over 8 all over 2. Everybody's okay with how I plug that in? First thing I'd want to do is multiply 2 times 3 pi over 8. So I'm just going to think about that as like 2 over 1. So it just kind of reduces the fractions as I go. So what I have is really 1 minus 3 pi, or cosine of 3 pi over 4, all over 2. And cosine of 3 pi over 4, that I can look up on the unit circle. So if I go to the unit circle to 3 pi over 4, pull the x-coordinate for cosine, that is negative root 2 over 2. Negative of a negative is positive. And then the last thing I'd want to do is simplify this a little bit more because I don't really love the fraction inside a fraction thing. So the easiest way to kind of do that simplification is I'm just going to multiply the top and bottom of this fraction by 2. So the 2 is going to distribute through. 2 times 1 is 2. 2 times root 2 over 2. The 2 in the numerator and denominator cancel and just leaves me with the root 2. And the denominator 2 times 2 is 4. I'll just leave it like that. Feel okay there? Not a big deal. Basically, we're just plugging stuff in, right? Hardest this could get would be maybe giving you something like this. So cotangent squared of negative 165. First observation I make is that I don't have a power reducing identity for cotangent squared, but that's okay. All I'm going to do is just use the reciprocal of the tangent one, because I know that tangent and cotangent are reciprocals, right? So I'm just going to use that idea. No big deal, right? Okay, so I have that this then is equal to 1 minus the cosine of 2 times negative 165 over 1 plus cosine 2 times negative 165. And if I multiply the 2 times negative 165, I get negative 330. Okay there? Now I observe that negative 330 is not a unit circle angle because it's negative. All of my unit circle angles are positive. What am I going to have to do to that?
Add 360.
Great. We're going to find an angle that's coterminal to this, that is on the unit circle. We would do that by adding 360. That's exactly right. So negative 330 plus 360 just gives me 30 degrees. And then I go to my unit circle and just look up that. So cosine of 30 is root 3 over 2. So far, so good. Same issue here. I got fractions inside of fractions. Let's clean that up before we get to a final answer. What should I multiply to the numerator and denominator to clear those fractions out of there? 2. Yeah. So I'll just distribute everything through. That's 2 minus root 3 over 2 plus root 3. Don't, oh, shoot. Here, I'm sorry, guys. I wrote down the wrong thing, right? I wrote it right up there. I don't know how I managed to write it wrong down here. I mean, let's go fix all those, because the next step, those are wrong, is going to be a bit of a problem. Okay. Sorry about that. I wrote it right up there. I just didn't take it with me. Okay. So this here is an answer, but it's not the best answer we can give. What could we do better? There's a radical in the denominator, right? So we'd prefer to have our answer with no radical in the denominator. Unfortunately, this situation, I have addition and subtraction of a radical in the denominator. So the way that I have to, or what I have to do to move that radical out of the denominator is I'm going to multiply the top and bottom by the conjugate of the denominator. So the conjugate is the same thing with just the opposite sign in the middle. And when I have two parentheses next to each other with multiplication in between, what I really should be doing there is foiling. So I'll write out the FOIL here. Note that root 3 times root 3 is root 3 squared, or just 3. Everybody so far so good? Plus root or 2 root 3 and minus 2 root 3, those will just add to give me 0. In the denominator, 4 minus 3 is just 1. In the numerator, 4 plus 3 is 7. And 2 root 3 plus 2 root 3, we just add the coefficients, gives us 4 root 3s. And because my denominator is 1, I don't even really need to hang on to it anymore. So 7 plus 4 root 3. So again, the actual trigonometry part was pretty easy, just plugging things in and pulling the unit circle values. Not too bad. We had some like tedious simplification afterwards, worrying about clearing out the fractions and then getting rid of the radical, but you know, not the end of the world. Everybody's okay with that though? Okay. The other thing that we might be or is useful with these identities is to do, we can use them to do like verifying proofs. So let's say we want to show that sine cubed is equal to 1/2 sine x times 1 minus cosine 2x. Hi, Eric. Thanks. So one of the rules that we had, or suggestions that we made when we talked about doing these verifying problems in chapter 5, was to start on the more complicated side. That becomes less appealing when we have these newer identities, because all of our new identities take something simple and make something more complicated out of it. So I really find that often it's easier to go from the simpler to the more complicated side when I have these new identities. So really I would be looking at working on the left-hand side here. Now, a sine cubed, I don't have any identities that specifically use a sine cubed, but I know I can just write sine cubed as like sine times sine squared. And that looks pretty good to me because I know I need a regular sine x anyways at the end, so that feels pretty good. Everybody cool with that plan? And since that sine squared is going to need to turn into like a double angle, seems like the power reducing is the way to go there. So I'll apply my power reducing formulas. That becomes 1 minus cosine 2x over 2. And hey, that's just about it, right? The only last observation that I'm going to make is dividing by 2, where I have 1 minus cosine 2x divided by 2. It's the same as multiplying by 1/2. And I know I can do that multiplication in kind of any order. So I can just take the divides by 2 and move it to a times 1/2. And that's it. We did it. That's not too bad. Oh, bye-bye. That's the box that I write at the end of my proof. Just colored in. Just like the period at the end of a proof. Emily?
So how did you get 1 minus cos like that for
That's my my power reducing identity. Cool. Okay. Great. The next set are these half angle identities. And again, we're going to just write jeepers creepers. a couple of these. Again, we're not going to write the like secant, cosecant, cotangent versions of these because they're just reciprocals. In particular, because the radical makes it like kind of a pain in the tuchus to write a reciprocal, because you worry about, hey, should I rationalize this denominator, and it gets pretty ugly pretty quick. So and just for the record here, we have 3 versions of the tangent one. So depending on what you're doing, you may want to choose any one of these 3. So depending on what you want to do. So let's just run through a couple of examples. Again, we're going to be finding the exact value using our half-angle identities. So let's say we want to do sine of 22.5 degrees. Now again, 22.5, not a unit circle angle, right? But notice that when we write the half-angle identities, we need to write it as something divided by 2. So what divided by 2 gives me 22.5? Yeah, that's 45 divided by 2. And 45 is a unit circle angle. So now we're good. So I have plus or minus square root 1 minus cosine 45 all over 2. Yes?
Sorry, how did we get the 45 over 2?
It's the same thing as 22 and a half.
How would I find that out, like, on a test? I don't.
Multiply it by 2.
Oh,
Is that okay? Okay. So let's right now decide whether we should have the plus or minus, right? We notice this plus or minus is here. The way we're going to decide is just using that 22.5 degree angle. So what quadrant is a standard position angle of 22.5 degrees? Quadrant 1, 2, 3, 4. That's in quadrant 1, right? Everybody agree? In quadrant 1, sign is positive or negative? Positive. So which one should I use? Yeah, we want the positive. Everybody okay with that? So not difficult to do, but you got to remember to do it, right? The only trick is that you use the original angle. You're not using the 45, you're using the 22 and a half. In this case, it wouldn't have really mattered, but if we did like cosine of 75, that's the same thing as cosine of 150 over 2. 75 cosine would give you a positive value. 150 cosine would give you a negative value. So you got to make sure you're using the original angle measure to decide positive or negatives. Okay? All right. So I'll go to my unit circle. Cosine of 45, I looked that up, and that is root 2 over 2. We okay there? Do we like that, the way to look at that answer? No, we got fractions inside of fractions, right? What should I do to get rid of the fraction inside of fractions? Multiply the top and bottom by? Close. It actually has to be the square root of 2 over 2, because I know if I multiply something under a radical and I want to multiply inside the radical, the thing I'm multiplying also has to be inside a radical, right? Like root 2 times root 3 gives me root 6. Root 2 times 3 just gives me 3 root 2. You know what I mean? So I do that, and that's going to give me root 2 minus root 2 over 4. Is everybody okay there? Elvis? I'm multiplying by root 2 over 2. Or 2, you know, the square root of 1, basically. Because what this is doing is now I can write it as now I can do that, right? Having both of them under the square root allows me to put it under one big square root, and then I can distribute things through. That's the piece that you needed? Again, that's subtle. Would it be one of those things that like is easy to miss. Anyways, going on here, there's one more little piece of simplification I can do with this. Notice that I have the square root of a fraction. The square root of a fraction is the same thing as the square root of the numerator over the square root of the denominator. And the square root of 4 is just 2. Is that okay with everybody? I would say that one thing to be cautious about here is that when we're drawing our radicals, we're making it really clear whether the radical is over the entire fraction or just over the numerator. I can only grade what you've written on your sheet of paper, even if I know that you mean something different. So just be careful when you're drawing those radicals that you're making sure you're being conscious of, is this over the entire fraction or just the numerator? It's easy to kind of get going fast and get a little bit sloppy with that. You know what I mean, guys? Okay. Let's do another one of these. Let's say we wanted to do cotangent of let's say 9 pi over 8. Okay. So how do I rewrite that as a half angle? What divided by 2 gives me 9 pi over 8? It's 9 pi over 4, right? Just multiply by 2. Just like we did before with the 22.5, we multiplied by 2 to get 45. I'll just multiply 9 pi over 8 by 2. Give me 9 pi over 4. I had to reduce, but like, I'm still doing the exact same thing, even though it's a yucky looking fraction. That's okay. Fractions are fine. Not a big deal. I can handle that. Everybody's okay? All right. So now I have my choice here. again, I'm going to use the reciprocal of one of these tangent ones, right? Since we're doing cotangent, I'm going to use the reciprocal of one of these. Which one would I want to use? They're all okay, but one of them's going to be a little bit easier to deal with than the rest of them. I definitely don't want the radical, right? With the plus or minus, that seems like the worst one to pick. That's the one that I want to use. Because if I have the choice, I'd rather not have addition and subtraction in my denominator. Remember, this is getting flipped because we're doing a cotangent problem. The reason is, if I get a radical in the denominator with addition and subtraction, getting the radical out is kind of a pain. So I'm just going to pick the one where I don't end up with any addition and subtraction in the denominator, because it makes dealing with a radical easier later on if I have to. Jack.
So if this was a tangent, just from tangent one, you would prefer to use the second?
The middle one, yeah. Yep, exactly.
Do the exact same thing with the
Yes, exactly. For the exact same reason, yes. So what do we have? We have 1 minus cosine of 9 pi over 4 over sine 9 pi over 4. Now you might have noticed 9 pi over 4, not on the unit circle. What am I going to do? I'm going to find an angle coterminal to it that is on the unit circle. To do that, I would, well, I wouldn't add 2 pi because it's too big right now. I'd be subtracting 2 pi, but right idea. So when I subtract 2 pi, that just becomes pi over 4. And rather than recopying that again, I'm just going to do that. Is everybody okay with what I did? Okay. So I'll go to my unit circle. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. And here's where, if I had done the other one, I'd be left with like 1 plus root 2 over 2 in the denominator, and that's kind of going to be a pain to deal with later on. By choosing this one, I just avoid a little bit of hassle. Right? Because to rationalize the denominator that's just root 2, all I need to do is multiply the top and bottom by root 2. And I acknowledge that you could have done those last 2 steps kind of all in one shot. But I figured it was going to be a lot easier to see what was going if I just did it in 2 separate pieces. You know what I mean? Instead of multiplying the top and bottom by 2 in that first step, I could have just done the root 2. And that would have cleared the fraction also. But that's a little bit harder to see why that would clear the fraction. And it would have rationalized the denominator in one shot. I did it as 2 separate steps, so because that would be my assumption of what you would do. Is that okay with everybody? And you see the reducing at the final step there? So let's do a proof here. Okay. So again, I would notice on the left-hand side, I have that half angle. I'm going to work on the left-hand side because I'm going to be looking to use a half angle identity to get rid of that x over 2. So notice that I actually have x over 2 squared. So I'm going to go ahead and do cosine of x over 2. So I use my half angle identity. But since it's cosine squared of x over 2, that piece needs to be squared also. Everybody cool with that? But I'm really excited that that squared is there because anything squared has got to be positive, so it cancels the plus or minus. And if I square a radical, that just kind of cancels out. Right on, my dudes. Right on. That's what I'm talking about. Doing good so far? Well, I have a times 2 and divides by 2. Get rid of that stuff. That all cancels out. We'll distribute the secant through. And we know cosine and secant are reciprocals. So we know those will multiply to give us 1. I skipped a little bit of steps there, but I think that that's one that we're okay with me skipping. That should be easy to see what I did there, right? What do you think? Everybody happy with that? Okay. So let's do a couple here from 6.4, which is just proofs and solving. So here in the previous sections, it's been kind of obvious what identities to use because it's been the identity that we were just studying. It was going to be like the key one to use. Here, let's look at one where really you could use a variety of identities to do this. So let's say we want to do prove 2 cotangent of 2 alpha is equal to cotangent alpha minus tan alpha. Now, I would be interested in working on the left side because I think that I have access to lots of these identities that involve a 2x or whatever. So what identities could I use here? If I have cotangent or 2 cotangent 2 alpha. If I look at my identities, I could use this if I think about 2 alpha as alpha plus alpha, right? Everybody's okay with that? So I could do that. I could use, oh, come on. Come on, pen. What are we doing? Excuse me while I unscrew my pen, take the battery out, and put it back in, because it is just decided just wanted to stop working. I don't know why I did that. Yeah. Or we could do the double angle. Which one looks like it's going to be easier to use? Yeah, I'm going to use the double angle, right? That seems much nicer than the addition or the sum or difference one. You guys agree? Okay. They'll simplify down. It wouldn't have really mattered, but so I'm going to have 1 minus tan squared over 2 tan squared. Well, that's pretty great because times 2 divides 2. Get those guys out of there squared away. And then I would probably just think about this now as 1 over tangent alpha minus tan squared alpha over tan alpha. So I'm just going to rewrite that fraction as 2 fractions with a common denominator. Is everybody cool with that? So I can reduce that one to just be tangent. And 1 over tangent, that's just the reciprocal identity of cotangent. And that's what I'm looking for. That's not so bad. Yeah.
So you got the 1 over tangent. That was just the one left over from the 1 minus tan squared.
Okay. So if let's just do like an aside here. If I have 1 plus 3 over 2, that's the same as 1/2 plus 3/2, right? Because it just gives me 4 over 2 and 4 over 2, right?
Yeah.
So that's all I'm doing here, is I'm taking that with this. So that's the same denominator. Those are my numerators. Does that see it now?
Yeah.
It's one of those things like when you draw it with just numbers, you're like, oh, yeah, of course you can do that.
Yeah.
But like seeing it with all the symbols there, it's like, hold on, what did you do? Yeah. Totally fine. If it doesn't make sense, please ask. Okay. So let's say we want to solve cosine 2x is equal to sine x. Now remember, when we had done the problem like this previously, if I have a coefficient on the x, this kind of makes it a pain in the butt, right? Because we have to start with the infinite solution and then use that infinite solution to generate the pieces that I need inside of any interval. Right? You guys remember doing that last chapter? The alternative that we have now to doing that, though, is I can just use my angle identities to rewrite this with all x's in it. And then when I never have to divide by 2. You know what I mean? Which is what I'm going to do here. So I'm going to start by deciding or finding an identity to use for cosine 2x. So if I go to my identity sheet, I could do this with, instead of 2x, I could write as x plus x. Probably not what I want to do, though. That looks kind of yucky, right? The other alternative is I can use this one, but here I have 3 choices. For this particular problem, which one of these 3 is going to be the best choice? I want the last one. Why? Because if I do that, I have only one kind of trig function in my problem, right? Just sines. That's why. Because if I have just signs in here, I can like move all this stuff onto one side. So I'll add the 2 sine squared and then subtract the 1 over. And now I have something that looks pretty quadratic, right? So we can factor that. We would want to find the 2 numbers that multiply to give me 2 times -1, and then add to give me 1. Well, hopefully it's pretty easy to see that's just 2 and -1, right? So I use those 2 numbers to rewrite the middle term as 2 sine x plus -1 sine x. We'll make our 2 groups. From the first group, we can take out a 2 sine x. From the second group, we can take out a -1. And now, since each term has a sine x plus 1 in it, we can factor that out, giving me sine x plus 1 times 2 sine x minus 1. And now that we're in factored form, we can apply the 0 product property and set each of these pieces equal to 0. And then solve. So x is sine inverse of 0. That happens at 0 and pi. Oh my goodness, that's not sine inverse of 0. You got to subtract 1 first, you dummy. Sine is -1 at 3 pi over 2. And the other one, we're going to add 1 and divide by 2. So sine inverse needs to be 1/2. That happens at pi over 6 and also at 5 pi over 6. So those are my solutions. Okay there? Notice at no point did we end up having to divide by 2 when we're doing the solving, right? Or divide x by 2, I should say. So we didn't change the coterminal stuff at all. The identity allowed us to avoid having to do that, which is pretty cool. Yeah, man, pretty cool. Let's do another, and then we'll be done for today. Sound good? So looking at this one, need to give us an interval. Let's do this over all real numbers. So let's go look at our identities, because the place that we want to get rid of is the theta over 2, right? So let's look at our identities and see what we can do with that. So I see 2 options. I can either use the power reducing, or I can use the half angle twice, right? Because it's sine squared of x over 2. I'd probably just use the power reducing. Oops, that was minus, I think. Everybody okay there? So those cancel and those cancel. So that's good. I got rid of all the coefficients on my thetas in the process. That's not so bad. Can I solve this the way it's written with a sine squared and then a regular cosine? What do I have to do? Well, I got to turn that sine squared into a cosine. Let's do that. Right? Sine squared is 1 minus cosine squared. That's the Pythagorean. Cool. I'm going to subtract 1 from both sides and then add cosine squared to both sides. So I have 0 equals cosine squared minus cosine. And now I can just take off a greatest common factor of cosine. And now that it's factored, we apply the zero product property. So I have cosine theta is equal to 0. Cosine is 0 at pi over 2 and 3 pi over 2. And then add 1 to both sides and then do my cosine inverse. Cosine inverse is equal to 1 at 0. So I'd say my final answer here is 0 plus 2 pi k. And then I can write it as 2 separate ones, or what I would do is I just write them together as one answer. I just write pi over 2 plus pi k. You could write them as 2 separate ones, both plus 2 pi k if you wanted to. That's still okay. Drake?
For cos 0 equal, what is that? X equals sign, I can't read that. Like,
Cosine 0.
you separated the two.
This thing is a 0.
Oh.
That's cosine of theta equals 0. Is that what you're asking? That was the spot? Okay. Lexi, did you have your hand?
Oh, never.
You're okay? Okay. Eddie, did you just stretch in?
Just stretch.
Cool. Okay. This feels like the place to stop. Just as a reminder here for Chapter 6, all of the things that I would have assigned in Chapter 6 are in the content library. So like you have the problems and the odd solutions, you have the worksheet and the key, the review and the key, the test version I would have given you and the test key. All of that stuff is there for you to look at. I think at minimum I would want to do the test, since the exam questions are coming directly from the test questions. So at minimum I'd want to do that, but if you're like, I think I still need a little bit more practice of something that's not the test question, there's lots of other stuff there that you have answers and worked out solutions to kind of pick from. Don't feel like you need to do all of it. Do enough to where it's like, okay, I got a handle on what's going on. It's not decidedly different than what we did last chapter. It's exactly the same techniques. We just have like a new set of identities that we can do stuff with, right? That in a way make the solving a little bit simpler, right? You trade a little bit of trigonometry out and get a little bit more algebra in. Usually that makes life a little bit easier, is to not have to worry about, because I divided this thing by 2, I really got, like you can ignore all that stuff and just do some more algebra, which I think is a good trade more often than not. Okay. Cool.